Okay, so in the previous screencast, I talked about there being four pieces of macroevolutionary evidence, or four pieces of evidence that support the idea that evolution is has happened and will continue to happen. The first of those was what did I do first? I can't remember now. I think I did the fossil record. The second one was boy, my Alzheimer's kicking in. Homologous structures. And then I mentioned at the end of that screencast that there were two others. The first one is ontogeny, and the second one is molecular evidence. So let's go ahead and take a look at this concept of ontogeny as evolutionary evidence. Okay, so as you can see from this drawing, essentially, I guess schematics more than anything else, ontogeny is the study of the development of an organism that typically starts with fertilization and runs through to the mature organism. And don't forget that one of the things that we use evolution to explain is the common ancestry piece here. Okay, so you can see here that if you look at each of these initial organisms, these sort of pre-fetal, very early stage organisms, that they look remarkably similar to one another. And in fact, you can see that once they actually develop a little bit further on in the womb, then they start to diverge significantly. But the fact that there are incredible similarities that exist in the very early stages of development for these organisms is an indication that there is a shared ancestry that exists, despite the fact that the completely mature organisms look very different from one another. The other thing that's kind of cool to think about here, if I were to draw lines right here, okay, many people would think that if you looked at something like well, perhaps this isn't as good as it could be, but oftentimes instead of using a tortoise, as you can see right here, they'll use a lizard of some sort. And most people would look at the form of a lizard and then look at the form of a mature salamander, and you don't see either of these things in this case. They would think that they were more closely related to each other than a salamander would be to a fish. But in fact, when you look at this ontologically, you can see that they actually share many more similarities, the salamander does, to the fish. And similarly, the reptiles, whether it's a tortoise or a lizard, shares a much closer resemblance to the bird family, in this case the chick here. Okay? All right, so again, that's a concept here that ontogeny supports the idea of shared ancestry. I think you can see right here it's very hard to ignore that there's clearly shared ancestry that exists. And then lastly, we have this concept of molecular evidence, and this is something that clearly has only more recently, and I say recently, in the last 20 or so years, which may not sound too recent for you, but it does for me, is something that is a really hugely burgeoning part of biology, is looking at the molecular connections that exist among organisms. So let's look at this data set. Now this goes back to our old pal DNA. And obviously, with DNA, we all understand the concept that DNA ultimately leads to the expression of proteins, and those proteins are what determine our characteristics. Now, that means if we take a close look at our DNA, we might be able to see some interesting things. Because if you could test every single sequence of DNA, it would make logical sense that species that are more closely related to one another would share the greatest amount of biochemical similarities, meaning that they would share, the DNA would be most closely related to one another, they'd be a closer match. And so this is sort of the central premise to this whole idea that molecules, or the biochemistry of the organism, helps to reveal the relationships, the connectedness, or the common ancestry of those organisms. So let's take a look at that and see how this matches up when you look at DNA. And also don't forget too that the way that an organism is going to evolve will happen at the molecular level. So changes or mutations in the DNA, which will either be neutral or they're going to be something that does lead to a change. The accumulation of those changes are going to be what allows for the change in the organism over many generations. Kind of a crazy thing to be thinking about. So let's take a look at this molecular evidence. As you can see here, we have these monkeys or apes or whatever you want to call them. And here's the human being that you can see hanging out in there. And if we do a genetic study and look at the DNA associated with each of these organisms, we would see that in terms of the difference that exists here between old world monkeys and chimpanzees, and if you throw humans into there, you can see that we are really closely related to chimpanzees, right? Obviously, a chimpanzee is going to have no difference that exists with itself. But if you compare the chimpanzee to the human being, you can see that there's only going to be about a 1.6% difference in the DNA between a chimp and a human being. There's a 2.3% difference between a chimp and a gorilla, etc., etc. And the mere fact that we have so little difference between ourselves and chimpanzees reveals our genetic connection that exists between chimpanzees. Now, does that immediately say to you that we must have evolved from chimpanzees? Well, if you believe that, yeah, absolutely, it could help support that concept because you clearly evolve from your DNA. So the DNA changing is what allows something to develop into a different species of ape. Now, the thing that people will probably be most bugged by is the fact that the humans are here. It really is kind of an arbitrary decision that was made here. We could have put humans in the chimpanzee position. Shoot, there's a phone call. Hold on. And this will be the last thing that I tell you guys. So, evolution. Oops. Terrible. The way we're going to define evolution in terms of the microevolutionary connection here is that it's the change in the genetic makeup of a population over time. And when we look at it from this perspective, we're actually looking at it from the level of the genes or the DNA, which makes up those genes. So it's the change of the genetic makeup here is the very important piece of this. And of course, if you change the genetic makeup, because we understand the central dogma, DNA to proteins, leading to the characteristics and traits of an organism, that's going to change the morphological or the physical structure or the behavioral situation of the organisms as well. All right, so stick that in your brain. We'll get back to it in future screencasts.